When someone mentions hours in the context of electric motor wiring, they are referring to revolutions per minute, or RPM. This is a measure of how fast the motor's shaft is spinning. Motors rated for over 50 RPM often need special attention when it comes to wiring to make sure they work correctly and don't overheat or cause other problems. There are several reasons for this. Firstly, increased centrifugal forces can come into play. When a motor spins faster, the centrifugal forces acting on its parts, especially the windings, get stronger. This can put extra stress on these components. Secondly, there is increased heat generation. Motors that rotate at high speeds produce more heat because of friction and other factors. This heat must be managed well to prevent damage to the motor. Thirdly, electrical noise can be an issue. High-speed motors can create electrical noise that can interfere with other devices or corrupt data in electronic systems. To deal with these challenges, motors designed for speeds above 50 RPM often require special features. One such feature is special insulation. Thicker insulation might be needed to handle the higher temperatures and centrifugal forces. Reinforced terminations are also important. Stronger crimp caps or solder connections may be used to manage the increased electrical currents and mechanical stresses. Cooling measures are often necessary. Fans or other cooling systems may be used to get rid of heat efficiently. Shielding can also be employed. Shielding helps to reduce electrical noise and protect other components from interference. Therefore, understanding these factors is important when dealing with motors that operate at higher RPM to ensure their safe and efficient operation. When wiring motors, one of the primary considerations is selecting the appropriate wire gauge and insulation type. The National Electrical Code, or NEC, provides tables such as 310.15, B16 and 310.16 that specify the allowable ampacities of insulated conductors based on their size, insulation temperature rating, and ambient temperature. It's crucial to select a wire gauge that can safely handle the motor's full load current or flow without overheating. For motors operating at higher RPM, which tend to generate more heat, it's often advisable to use wires with higher temperature ratings like 90 degrees Celsius or higher. This ensures that the insulation doesn't degrade prematurely due to the elevated temperatures. Additionally, the type of insulation should be suitable for the environment in which the motor is operating. For instance, if the motor is located in a damp or corrosive environment, moisture-resistant or chemical-resistant insulation should be used. Another critical aspect of motor wiring is the proper termination of conductors. As mentioned previously, reinforced terminations are often necessary for motors operating at higher RPM due to the increased mechanical stresses. This might involve using high-quality crimp connectors or solder connections that are designed to withstand vibration and thermal cycling. It's also important to ensure that the terminations are properly insulated to prevent short circuits or ground faults. In addition to wire gauge and terminations, grounding is a crucial safety consideration when wiring motors. The NEC requires that all motor frames be properly grounded to provide a low impedance path for fault currents. This helps to protect personnel from electric shock in the event of a ground fault. Grounding can be achieved by connecting a grounding conductor from the motor frame to the equipment grounding conductor in the circuit. The size of the grounding conductor should be determined based on the size of the circuit overcurrent protection device. Overcurrent protection is another essential aspect of motor wiring. Motors should be protected against both overloads and short circuits. Overload protection is typically provided by an overload relay or thermal overload device that is sized to trip at a current slightly above the motor's FLA. Short circuit protection is provided by fuses or circuit breakers that are sized to interrupt high fault currents quickly. The NEC provides guidelines for selecting the appropriate overcurrent protection devices for motors based on their type, horsepower, and voltage. When dealing with motors operating at higher RPM, it's particularly important to ensure that the overcurrent protection devices are properly coordinated to prevent nuisance tripping. This may involve using time delay fuses or inverse timed circuit breakers that can withstand the motor's inrush current without tripping. Furthermore, the wiring methods used for motors should comply with the NEC requirements. Depending on the application, motors may be wired using rigid metal conduit, electrical metallic tubing, flexible metal conduit, or cable. The wiring method should be suitable for the environment in which the motor is operating and should provide adequate mechanical protection for the conductors. In addition to the electrical aspects of motor wiring, it's also important to consider the mechanical aspects. Motors should be securely mounted to a rigid base to prevent vibration and misalignment. The motor shaft should be properly aligned with the driven equipment to prevent excessive wear and tear on bearings and couplings. Flexible couplings may be used to accommodate slight misalignments and reduce vibration. Finally, it's essential to follow all applicable safety procedures when wiring motors. This includes energizing the circuit before working on it, using appropriate personal protective equipment, and verifying the absence of voltage before making any connections. Only qualified electricians should perform motor wiring work to ensure that it is done safely and in accordance with the NEC requirements. When considering motors operating at higher RPM, additional factors come into play. Firstly, vibration management is essential. High-speed motors can generate significant vibration, which can lead to premature failure of the motor, driven equipment, and surrounding structures. To mitigate vibration, several strategies can be employed. One approach is to use vibration isolation mounts, which are designed to dampen vibrations and prevent them from being transmitted to the surrounding environment. These mounts typically consist of rubber or elastomer elements that absorb vibrational energy. Another strategy is to balance the motor's rotor dynamically. Dynamic balancing involves measuring the vibration of the rotor while it is spinning and then adding or removing weight to correct any imbalances. This ensures that the motor runs smoothly and with minimal vibration. Secondly, lubrication is critical for high-speed motors. The bearings in these motors are subjected to high speeds and loads, which can lead to increased wear and heat generation. Proper lubrication helps to reduce friction, dissipate heat, and extend the life of the bearings. The type of lubricant used should be specifically designed for high-speed applications and should have the appropriate viscosity and additives. The lubrication schedule should also be carefully followed to ensure that the bearings are adequately lubricated. Thirdly, cooling is often a major concern for high-speed motors. As mentioned earlier, these motors generate more heat due to friction and other factors. If the heat is not effectively dissipated, it can lead to overheating and premature failure of the motor. Various cooling methods can be used depending on the size and design of the motor. Air-cooled motors rely on fans to circulate air over the motor's surface, dissipating heat through convection. Liquid-cooled motors use a liquid coolant, such as water or oil, to absorb heat from the motor and transfer it to a heat exchanger. The heat exchanger then dissipates the heat to the surrounding environment. Fourthly, noise reduction may be necessary for high-speed motors, especially in noise-sensitive environments. High-speed motors can generate significant noise due to the rotation of the rotor and the interaction of the motor's components with the air. Noise reduction can be achieved by using sound-absorbing materials such as acoustic foam to enclose the motor. Vibration isolation mounts can also help to reduce noise by preventing vibrations from being transmitted to surrounding structures. Additionally, some motors are designed with noise-reducing features, such as skew rotors or optimized fan designs. Fifthly, electrical noise mitigation is often necessary for high-speed motors. As mentioned earlier, these motors can generate electrical noise that can interfere with other equipment or corrupt data in electronic systems. Electrical noise can be mitigated by using shielding, filtering, and grounding techniques. Shielding involves enclosing the motor and its wiring in a conductive shield that blocks electromagnetic radiation. Filtering involves using filters to block unwanted frequencies from the motor's power supply and control signals. Grounding involves providing a low-impedance path for electrical noise to dissipate to ground. Sixthly, control systems for high-speed motors may require special considerations. High-speed motors often require precise control of their speed and torque. This can be achieved by using sophisticated control algorithms and feedback sensors. A control system should be designed to prevent overspeeding, which can damage the motor and driven equipment. It should also be designed to provide smooth and stable operation over a wide range of speeds and loads. When dealing with high-speed motors, it's crucial to consult with the motor manufacturer and follow their recommendations for installation, operation, and maintenance. The manufacturer can provide valuable information about the motor's specific requirements and limitations. It's also important to ensure that all applicable safety standards and regulations are followed to prevent accidents and injuries. Remember, only qualified electricians should perform motor wiring work to ensure that it is done safely and correctly. Firstly, let's talk about wire selection. Choosing the right wire is important for any motor, but especially for those running at higher RPM. You need to consider the motor's full load amperage, or flow, and the ambient temperature where the motor is located. NEC Table 310.16 is your friend here. It tells you the maximum amperage different wire sizes can handle safely based on their insulation type and temperature rating. For higher RPM motors, you might want to go with a wire that has a higher temperature rating, like 90 degrees Celsius, to handle the extra heat. Secondly, consider the type of wire insulation. THHN and THWN are common choices, but there are others. THHN is good for dry locations, while THWN is suitable for wet locations. If the motor is in an area with oil or chemicals, you'll need a special type of insulation that can resist those substances. Thirdly, proper termination techniques are crucial. High RPM motors can vibrate more, so your wire connections need to be solid. Use crimp connectors that are properly sized for the wire and the terminal. Make sure to use a good quality crimping tool to get a secure connection. You might even consider using locking terminals that won't loosen over time. Fourthly, grounding is non-negotiable. A good ground connection is essential for safety. Connect the motor's frame to the equipment grounding conductor in the circuit. The size of the grounding conductor should be based on the size of the overcurrent protection device, like a circuit breaker or fuse. Fifthly, overcurrent protection is what protects the motor from damage if there's a fault or overload. You'll need both overload protection and short circuit protection. Overload protection is usually provided by an overload relay or thermal overload device. It's sized to trip at a current slightly above the motor's FLA. Short circuit protection is provided by fuses or circuit breakers. They're designed to interrupt high fault currents quickly. Sixthly, NEC guidelines are your friend. The NEC has specific guidelines for selecting overcurrent protection devices for motors based on their type, horsepower, and voltage. Table 430.52 is a good place to start. It tells you the maximum size of the overcurrent protection device allowed for different types of motors. Seventhly, wiring methods need careful consideration. How you run the wires to the motor is important. Rigid metal conduit, electrical metallic tubing, flexible metal conduit, or cable are all options depending on the situation. Make sure the wiring method you choose provides good mechanical protection for the wires. Eighthly, mechanical considerations are important too. Mount the motor securely to a rigid base to minimize vibration. Align the motor shaft properly with the equipment it's driving. Use flexible couplings to help absorb any misalignment. Ninthly, safety first always. Before working on any electrical equipment, de-energize the circuit. Use proper personal protective equipment, like gloves and safety glasses. Double check that there's no voltage present before you start making connections. Tenthly, consult the motor manufacturer. They can give you specific recommendations for wiring their motor, including wire size, termination methods, and overcurrent protection. They might also have specific requirements for grounding and bonding. Always follow the manufacturer's instructions. Remember that electrical work can be dangerous. If you're not comfortable working with electricity, hire a qualified electrician to do the job. They'll have the knowledge and experience to wire the motor safely and correctly. It's always better to be safe than sorry.